Okay, welcome to the morning session. So Madhava Hall today will have a quantum hall day. And so the morning will be supersymmetric and the evening will be non-supersymmetric. And I heard from the organizers that that is the way it was planned. So I have been asked to chair the morning session. So David just told me that I am not a very good timekeeper, going by how I did in my own talk. So it's a great pleasure to welcome David Tong, a longtime friend, to talk about supersymmetric quantum.
Thank you. Thanks, Gelton. Firstly, can I say thank you to Shubro and all the other organizers for inviting me and for putting this together. It's been a wonderful workshop, and it's just been wonderful to come to Bangalore and to ICTS for the first time. So I hope this is the first of many visits. I'm going to tell you about a paper that I wrote a few months ago and some work that's currently in progress. And to start with, I just want to tell you about the motivation for this work, because I'm sure there's lots of condensed matter physicists in the audience shuddering at the idea of supersymmetry and quantum Hole being put together. So I just sort of want to explain why I think this is an interesting thing to do. My impression is that with broad brush, the kind of questions that condensed matter physicists are interested in are very, very similar to the kind of questions that high-energy physicists and string theorists are interested in. For the most part, the questions are just, what does quantum stuff do when the interactions become strong? And there's a common language. The common language is field theory and RG, as we've heard in many talks. But in detail, some of the tools that have been developed are very different between these two fields. And one of the primary tools we have from a high-energy physicist to understand strong interactions is supersymmetry. So what I'd like to do, sort of in the spirit of this conference, is see if it's possible to take some of these tools from one area and apply it to different areas. And I'm sure this can go both ways. I'm sure there's lots of money to be made by taking ideas from condensed matter and applying to high energy, or vice versa. But in this talk, I just want to try and take some ideas from supersymmetry and apply it to a condensed matter context. I suspect most people here are condensed matter physicists. Who puts papers on HepTH? Okay, good. So for the people that didn't, oh yeah, Subir of course is both. For the people that didn't put their hands up, let me just explain what supersymmetry is. There's two places in high energy physics that supersymmetry plays a role. So the idea of supersymmetry is that you have a quantum field theory, and there's a fairly remarkable symmetry between the bosons in the theory and the fermions in the theory. Okay, so the theories have to have equal number of bosons and fermions, and there's literally a symmetry of the action where the boson turns into the fermion, and the fermion turns into, well, the derivative of the boson. So there's a symmetry between these two things. And the two reasons to be interested in this, the first is that supersymmetry might be a symmetry of nature. In fact, it's been sort of the prime candidate for what will be seen beyond the standard model once you finally turn on a particle accelerator that probes those regimes. Now, of course, we have a particle accelerator that's turned on and is probing those regimes, and there's no sign of supersymmetry whatsoever. So that first reason might die in the next couple of years, but you never know. The second reason to be interested in supersymmetry has nothing whatsoever to do with the LHC, and it's the reason that the people who do post papers on HepTH care about. It's that if you take a supersymmetric field theory, that can be very, very strongly coupled, so the interactions are strong, and usually you wouldn't have a hope in hell of understanding what's happening. If you add supersymmetry, it just gives you enough power to solve that theory analytically, so to figure out exactly what's going on. So this was first understood, I think, in the 1980s, but it was really in the 1990s with the work of Ashok Sen and later the work of Seiberg and Witten, who really sort of developed this and turned it into an art form where you can really start to understand things like the spectrum of strongly interacting field theories and correlation functions, and more recently even partition functions for strongly interacting theories. So it's in that context that I want to use supersymmetry here. It's going to be a toy model that's very closely related to the kind of theories that condensed matter physicists would care about, but with this extra symmetry, or in fact it's really just a little fine-tuning, we'll be able to say exact things about this field theory beyond what you could usually do. Okay, so that's really the motivation. It's worth sort of pointing out why supersymmetry doesn't appear in condensed matter physics that much, and I think there's might be obvious, but again, there's two places supersymmetry could appear. The first is that you could have a condensed matter system which just happens to have supersymmetry in the infrared. The effective description is supersymmetric, and Kedar told us about a candidate yesterday. I know Ashwin Vishwanath has written papers on this in recent years. So there's certainly a possibility that supersymmetry is realized in condensed matter, but I'm not going to take that perspective here. Instead, I'm going to take the perspective that a supersymmetric theory is just easier to deal with and will give us a good toy model to understand various systems. Okay. I should also, before I turn the slide, I should also say most supersymmetric theories are relativistic and are supersymmetric only when you have zero density and zero temperature. So that's usually not very interesting for a condensed matter perspective. As soon as you turn up the temperature, as soon as you turn on a chemical potential, supersymmetry is broken and you just lose all control over the interactions. It turns out that there's an exception to this, and this is what I'm going to tell you about. There is a theory in 2+1 dimensions, which is non-relativistic and at finite density of matter, but is still supersymmetric. And it's quite surprising. This theory isn't well known. It was discovered back in 1991, I think. It's 25 years ago. And it just seems to have been ignored by my community and by the condensed matter community. So I sort of rediscovered it earlier this year. And I think it's interesting. I think it contains a lot of interesting physics that we can extract from it. It's a theory in 2+1 dimensions, and it's a Chern-Simons-like theory. So it's perhaps no surprise that the physics that's contained in this theory is the physics of the fractional quantum Hall effect. So this is the theory I'm going to discuss, and we'll see the physics of all the things you know and love from condensed matter sort of emerging as we study this theory. Okay, so for the people that put their hands up, let me tell you about the fractional quantum Hall effect. This is an older version of the data that Senthil showed. And I'm not going to embarrass myself by trying to explain it. I'll tell you about well, okay, if you don't know what the fractional quantum Hall effect is, we'll see it emerging as we go through the talk, but basically this is what you need to know. You take electrons, they move in a two-dimensional plane, you put a magnetic field that way, and you cool the system down so that quantum effects become dominant, and if you do that, cool stuff happens. Okay, that's really the essence of the effect. And the cool stuff involves the particles that move around have a charge which is a fraction of the charge of the electron. So the electrons seem to split into many objects which move around. These particles also carry a fraction of the spin of the electron, so they're not fermions or bosons, but they're anyons. In very, very cool quantum Hall plateaus, the splitting is a non-Abelian splitting. So the anyons have this thing called non-Abelian statistics. So there's lots of wonderful things that happen here. From my perspective, I'd like to tell you about the theory, because the theory behind this is also this wonderful network of different ideas that approach the problem from slightly different points of view, and these kind of different points of view connect in interesting ways. So this started about 30 years ago with Laughlin writing down wave functions for the electrons. So really a microscopic viewpoint of what these states, these fractional quantum Hall states are. But subsequently, there were lots of extra developments. Things like a Chern-Simons theory, which describes the long wavelength description of these fractional quantum Hall states. On the edge of the sample, there's a conformal field theory, so massless particles which move around. And Jainendra taught us about the composite fermion approach, which relates different quantum Hall plateaus. So there's really this wonderful network of very rich ideas which interconnect in different ways. And given that, there's 30 years of brilliant physics on this, I kind of feel a bit daunted trying to tell you something new. So I'll try and explain what the punchline is, at least for the first part of the talk. There's going to be two parts of this talk. The first part's going to be about the Abelian quantum Hall effect, or Abelian quantum Hall states, and really just Laughlin states. So states at filling fraction 1 over k. And the second part, I'll talk about some non-Abelian quantum Hall states, which is really what the purpose of this project was. Let me tell you the punchline for the first part, the punchline for the Abelian bit. Because, as I've said, 30 years we've known about the Laughlin state, so it's very hard to say something new about Laughlin wave functions. So I am going to have something new to say, but I should warn you now, it's going to be very modest, what I have to say, but I'll try and explain. So the new things I'll have to say is firstly, I'll give a very direct relationship between the microscopic wave functions and the effective Chern-Simons theory, in a way which I think is novel, which I think has not been done before, although there are many more experts in the audience than me, so I'd be interested to know. The second thing we'll do is we'll write down a wave function for the Laughlin state, but it won't quite be the Laughlin wave function. It'll be very close to the Laughlin wave function, but it'll be subtly different, and it'll be different in a way that's better, okay, in a very precise sense. You see, the Laughlin wave function isn't God-given, it's Laughlin-given, and it's not even the right wave function to describe the systems in nature. It just happens to be a wave function that you can write in a short space on a piece of paper. That's really what's important about it. But although you can write it in a short space, it's very hard to do anything with it, okay? Because it's a wave function of a macroscopic number of particles, which means if you want to compute an observable of any kind, you have to take an overlap, and you have to do a macroscopic number of integrals. And those integrals are very, very difficult to do. So Laughlin, when he first introduced this, explained a clever way to get around this, which is called the plasma analogy. So it's a way in which you take those integrals of computing overlaps of wave functions, and you reinterpret that in terms of a statistical mechanics problem for a two-dimensional plasma, which doesn't make the maths any easier, but it does give you some intuition for what these integrals should do. It means that you can put these on a computer, and you can ask your numerical friends who simulate plasmas what kind of phase this system is in, and you can get enough information from that to extract the physics that you like. But there is this crucial step in all of this early quantum Hall work where you have to rely on this analogy and rely on numerics to tell you what's happening. And this was a stumbling block for later work, because for non-abelian states, there wasn't this analogy, or it was much more difficult to construct such an analogy, and it really made it difficult to understand things like braiding of non-abelian anyons. So what I want to tell you here is that there's a simpler state. I think simple is the right word. It takes a little longer to write on a piece of paper, but it's better in the sense that you can actually do these overlap integrals analytically, and so you can compute the things that you want to compute, in particular the braiding of anyons. They're only abelian anyons, but you can compute the statistics analytically without relying on any kind of plasma analogy. Okay, so that's the payoff from the first bit of the talk. Please.
Wasn't that done analytically earlier also?
I think there have been approaches that have done it analytically, and I haven't understood them. But no, they needed the plasma analogy at a crucial step, and I'll explain as we go on. Yeah. But no, they absolutely needed the plasma analogy. The work I'm thinking of was done about 10 years ago, and it involved high-powered mathematics that was beyond me. Okay, the other thing I want to say, I'm going to try and make this accessible for everyone. That means that some of you will definitely be bored in places, and some of you will definitely be lost in other places. But I'm going to try. But please do just bombard me with questions. There are many people here who know much more about the quantum Hall effect than I know, and so I'm hoping this talk is for my benefit as much as your benefit. And really tell me, what I'm doing wrong or what the right questions to ask are as we go along. Okay, good. Are there any questions before I get going? Okay, so let me just jump in and tell you what the Lagrangian is we're doing. I've been to a bunch of condensed matter talks now. Every string theory talk starts with, here's the Lagrangian we're going to deal with. This never happens in condensed matter, right? It's always, here's a lattice picture. Okay, this is the Lagrangian we're going to deal with. It's something which is very familiar from long wavelength descriptions of quantum Hall effect. It's a Chern-Simons theory. It's just a U1 gauge theory, and it's a Chern-Simons theory at some integer level k. Okay? The slightly different thing is that we have both non-relativistic bosons and non-relativistic fermions coupled to this Chern-Simons field. This is not the external electromagnetic field. We'll see where that emerges later. So this is you usually call this little a, right? Okay. So this is usually called little a in the condensed matter literature. Yeah, it's not external.
So does this mean that these are actually not bosons or fermions?
Yeah, of course they're anyons. Yeah. But they have spin which differs by a half. That's really the meaning of it. This is Grassmann valued. This is not. Okay. So it's really a combination of two kinds of theories that have been proposed in the condensed matter literature. The usual long-distance effective Hall description is in terms of a boson, but there was a related theory by Fradkin and Lopez who wrote it in terms of a fermion, and this is just a combination of the two. Okay. And B is the gauge field associated to this, so it's F12. Okay, it's the magnetic field associated to A, which is not the external magnetic field. The external magnetic field is going to be called BX later. Okay. Yeah, it's hidden in the covariant derivative, which sits here and here. So the bosons and fermions couple minimally to.
No, so is that a reason why the K that is in the interaction term is the same as the K there?
Perfect, good. So that's really the key point of this Lagrangian that's going to make it special. So if you were a condensed matter physicist, you would just put some arbitrary coefficient here. The thing that relates this to this is the need for supersymmetry. Okay, so let me just explain briefly. This Lagrangian here has two supersymmetries. One of them I'm going to call Q1, one of them I'm going to call Q2. The details are not going to be important. If you want to know, I can tell you, but basically each one takes a boson and turns it into a fermion, and a fermion and turns it back into a boson. So there's two symmetries. The Q's are Grassmann objects, and the anti-commutator of the first Q gives you the particle number. That's the number of phi's plus the number of psi's. And the commutator of the second Q gives you the Hamiltonian.
The sum of both fermions and
Both
bosons.
fermions and bosons. And the anti-commutator of Q1 and Q2 gives you the momentum that you get from this. Okay. So there's a nice structure here. This theory was first written down by Leblanc, Lozano, and Min almost 25 years ago. I have a small contribution to this Lagrangian. My contribution is this term and this term. Okay, so the terms that have mu in there. So this is a chemical potential that we're going to add to the Lagrangian. Okay. For the people that came to the Goa conference, I talked exactly about this theory, except I set mu equals to 0. So it turns out when mu is equal to 0, this theory has a much larger superconformal symmetry of the Schrödinger type, and you can solve it using supersymmetric methods. So that was the topic in Goa. If you turn mu on, that drives this system to a fractional quantum Hall state, and that's what we're going to look at. K has to be an integer, and we'll see that explicitly when we quantize later. Sorry, say that again? Is M the same? Oh, sorry, N is the number of bosons plus the number of fermions. So it's phi dagger phi plus psi dagger psi. Oh, I see. Yes, so that's true in this system. That's right, yes. Yes. It's not true if you add more flavors, but yes, in this system it's true. Thank you. Yeah, please. No, the electrons are going to be the vortices of this, which is the standard story in effective theories of quantum. We'll see. We'll see what mu does later. Yeah. Are they also nothing's a spinner here. Psi doesn't have a spinner index. Oops. The fermion doesn't have a spinner index, and Q1 and Q2 don't have a spinner index either. You can derive this Lagrangian from the kind of things you know and love. To take the n equals 2 relativistic Chern-Simons matter theory, and there's a way to turn on a chemical potential so you keep the particles and throw away the antiparticles. This is what you end up. Senthil.
The thought usually in the supersymmetric Lagrangian, every gauge field also has a superpartner.
That's true, but what supersymmetry really requires is that the propagating modes have superpartners, and the gauge field in a Chern-Simons term doesn't propagate. So yeah, it's quite surprising. The gauge field is a supersymmetric singlet, and phi and psi turn into each other. For the purposes of this talk, all you really need to know about supersymmetry is exactly what we heard earlier. It's that this coefficient here is related to this coefficient here, and that's going to be the key bit of physics that allows us to solve things as we move forward. Okay, so it's just a fine-tuned Lagrangian from that perspective. That's right. It's got just 1 and 2. Oh, sorry. This is complex. So it's P1 plus IP2. Yeah. Sorry. Good. Other questions? It's what you get by taking the non-relativistic limit of the n equals 2 theory. Yeah. Yeah.
So the local operator in this case, gauge invariant local operator is a sum of the psi dagger psi. And is that the thing that you're going to couple to the
No, the fermions are going to disappear from the game very shortly, actually. Yeah.
But there is such an operator.
There is such an operator. Yeah. We'll see. Okay, so that was the original Lagrangian. There's one extra thing I want to add, which is this is a Lagrangian for particles moving on a plane. And you know, I don't know much about condensed matter physics, but the idea, I think, is that the matter should be condensed in some way. So you know, when you put stuff on, you have to squeeze it together, okay? And if it's just on a plane and can wander anywhere, it's not going to do anything interesting. So what we're going to do is add to this a potential which breaks translational invariance. So it's just going to be a harmonic trap which pushes everything towards the origin. The trap takes a particularly awkward-looking form. It's probably not what you would have written down. It turns out that if you add this combination of things, which is very unnatural, this still preserves supersymmetry. So there's a way to add a trap which preserves supersymmetry. For the few string theorists in the audience, it's analogous to the omega deformation in relativistic theories. I suspect, although I haven't proven, if you started with the n equals 2 relativistic theory with an omega deformation and then took the non-relativistic limit, this is what you would get. It's very similar. We'll see later, actually just this term is going to be the important one, so that anything that carries some flux, you can see is going to be pushed towards the origin. That's the essence of it. Z is x plus iy, yeah, thank you. Yeah. Okay, so this is going to be the Lagrangian that we're going to solve. So let me tell you some basic... Yeah, it's a different trap from the one I was talking about in Goa, actually. Oh, okay. Yeah, it's not the same one. Yeah. Okay, so what's the physics? The vacuum is the following. The vacuum, maybe, yeah. Okay, so let's look at the potential here. Forget about the trap for now. If you set the fermions to 0, you can see that the vacuum is minimized by, you've got essentially a negative mass term here, if mu is positive. So the bosons want to condense in the vacuum. So the vacuum is given by... you know, it's a good question. It turns out actually... Yeah. Okay, I remember. This one is preserved and this one isn't. Yeah, that's what happens. The trap is not invariant under this one, but it is invariant under this one. But this one, as we're about to see, was spontaneously broken anyway in the vacuum, so you actually didn't care about it. This one's going to be doing all the heavy lifting. Yeah, thank you. Okay, so this is the vacuum, and you can see now that Q1 is broken precisely because you've got a non-zero particle number in the vacuum. So the vacuum has a non-zero flux B, but the bosons condense. And you can just look at what the excitations around this vacuum are. So there's two sorts of excitations. There's one for the boson and one for the fermion. And both of them are gapped in this theory. And both of them have a gap with energy that's proportional to mu. But there is a gapless excitation, which are the vortices. And the vortices are going to play the role of electrons in this theory. So again, it's very standard from condensed matter, going back to the early 1990s, that if you have a Chern-Simons theory with an integer-valued Chern-Simons term, it's the vortices which you should think of as the electrons. Okay, so why are there vortices? Phi condenses in the vacuum, which means the phase of phi can wind, and the phase of phi winding is going to be precisely these vortices. Okay, just a very basic thing. The vortices are going to be bosons when k is even, and fermions when k is odd. This follows from standard flux attachment arguments, which if you know, you know, and if you don't, I won't explain. But it means that we're going to talk about the quantum Hall effect for fermions, but also the quantum Hall effect for hardcore bosons at the same time, depending on whether k is even or odd. Okay. Now comes the key point. These vortices are very special. These vortices are what we call in string theory BPS. And I'll try and explain physically what that means. The first thing is that the equations the vortices have to obey are not, as you might imagine, the second-order equations of motion that come from that Lagrangian. They're much, much simpler. So the vortices that the equations obey is this equation here, which is actually just Gauss's law from the previous Lagrangian, and this equation here. And this one, as you can see, is a first-order equation to second-order equation. So you can prove that if you can solve these two equations, these are solutions to the full equations of motion from the previous Lagrangian. But something very special has happened. So let me try and explain what's going on. Subir.
Phi, as we noted earlier, were actually any odd, but they're condensing anyway, or should I think of it as like condensate of pairs of any odd?
Like in both boson here, condense the phi, the way
Yeah, but they're actually boson.
they're pure too.
No, I don't know. If I take the action, like 1 over k plus 1 of
So the bare type field case is like in boson boson. Boson sector is just like exactly the same.
yeah.
If I'm working classically, as I am at the moment, we'll do quantum effects later. This is clearly the classical ground state of the system. Okay, so what's special about these vortices? These same equations appear when you look at abelian Higgs models describing superconductors. And what's special is the coefficient of that potential, the thing that was related to K, has been tuned so that you're exactly halfway between a type 1 superconductor and a type 2 superconductor. That's the fine-tuning that supersymmetry has given you. So the vortices that exist in this theory experience no forces whatsoever. Okay? Neither attractive nor repulsive forces. So that's the physics. Mathematically, what happens is when you do that, the equations for vortices simplify, and mathematically they become much richer. So you have first-order equations rather than second-order equations. And in particular, if you look for a solution with n vortices, so that means phi winds n times, an infinity, there's not a unique solution, there's a manifold's worth of solutions. So the solution with n vortices has parameters in there, in fact 2 n parameters, that basically tell you the positions of these n vortices. And you can put the n vortices here, or you can move them slightly, and you still get a solution to the equations of motion. Okay? So that's really what's special in this theory, is the vortices are fine-tuned not to have any forces. It's just true that if you plug this into the Hamiltonian, it's 0. Again, it's related to the fact that they're at this special fine-tuned point. But it's just a fact. We'll see. It's all going to be about quantizing this ground state and understanding what it is. You need to insert some energy to get the fermions because they're gapped. And in fact, I'm going to throw them away from now on. So we're not going to discuss the fermions. It's really just going to be the dynamics of the vortices. Okay, so let me try and spell out the key idea. Sentil.
Sort of hung up on this issue that I was talking about earlier.
What was that?
Go back to your Lagrangian.
Yeah.
So the gauge and weight, there is a gauge and weight in fermion operator in this case.
Yes.
Right. So your theory really lives in a fermion microscope.
Hang on, it's phi dagger psi.
Right.
Okay.
That's a gauge and weight in fermion operator.
It's true. It may help that it annihilates the vacuum because there are no antiparticles in this theory. So psi annihilates the vacuum, and psi dagger creates fermions. I don't know if that helps with your question, but it's a true statement.
No, so the
Hilbert
Hilbert space in which all of this is going to play out is a fermion space. I mean, there are local particles.
Yes.
Microscope, the basic particles.
The fermions are going to be gapped. If you're really worried, take this Lagrangian and throw away all the fermions, but keep this fine-tuning. Everything I say will carry on. Does that make you feel better?
Or throw away, set the fermion number.
Yeah.
So why did you need the fermion?
Well, I kind of needed them for a psychological crutch almost. That I knew there should be a supersymmetric version of the quantum Hall effect somehow. And the goal was to try and construct the theory which had it, and I got it, but once you get it, it turns out the fermions are less important than you think. Yeah. So this is going to be the key, this fine-tuning. Okay. Sorry, I didn't hear Loga.
You see the fermions needed to protect it to keep that coupling there.
Do you know, it's different from relativistic theories, because in relativistic theories, the loops of the fermions affect the bosonic sector, but they're loops of particles and antiparticles. And here there are no antiparticles. So actually the loops of the fermions aren't needed in the same way as they are in a relativistic context. Yeah, we'll see as we go along where things appear. Okay, so let me just try and spell out the key idea that's going on here. Let's throw in n vortices, and ultimately n is going to be a macroscopically large number. Okay? And we've already seen that these vortices can sit anywhere and you still have a solution to the equations of motion. So the first thing to state is something which is pretty straightforward. That there's a chemical potential for electric charge, but if you're a vortex, you experience a chemical potential for an electric charge as a magnetic field for you. Okay? So because of this chemical potential, the vortices feel like they're moving in a magnetic field. And it's trivial to show. This is the chemical potential term that was in the Lagrangian. You do an integration by parts and you rewrite it like this. The J mu is the current for vortices, and this is an external gauge potential which takes the following form, which is precisely the form for a magnetic field of this strength. Okay? So mu was a chemical potential for electric charge, but really you should think of it as an external magnetic field for the vortex excitations. So we're kind of in the quantum Hall regime. We have these vortices moving around, but they're moving in a magnetic field. Okay. Now the key idea is the following. We'll put these vortices in a trap, and what happens is they get squeezed together. But these are solitons, so these are solutions to some nonlinear equations. They're not point particles. And as they get squeezed together, they don't sit on top of each other, but when you solve the equations, as one vortex comes on top of another, it spreads out, and it forms a very big disk. Okay, so if you put n of them together, you get a large disk of big vortex stuff, and this is the ground state of the theory. So already, classically at least, I've eliminated the degeneracy just by squeezing them together. And so these are actually numerical plots of the solutions. On the left, there's just 7 vortices put on random places. On the right, it's actually the solution for 70 vortices, but all squeezed together. Okay? And you can see what happens is you actually have this big droplet disk of stuff where you access a different phase, which is inside the vortex. Okay? You can show that all of these states have yes, actually, this is the unique zero energy state now in the presence of a trap. Yeah.
Is the density uniform?
Density is uniform, yes. Yeah.
Why is that? Because there's not a trap.
The trap was designed in a very special way. So the trap is actually gives an energy to the states that's equal to its angular momentum. And this is a vortex which has 0 angular momentum. So I designed the trap specially so it had this property. Again, it was related to the fact that the trap was consistent with supersymmetry. That's how I knew that was the right trap. It's a classical statement at the moment. We'll do the quantization later. Okay. So the size of this this object goes as the square root of the number of vortices. This is the radius of the droplet. And as Janendra mentioned, it's uniform. So what's really going on here is the following, that if you have n vortices, say you have 70 vortices, you put them all on top of each other, in the very center there's a 0 of the Higgs field that's a 0 of order 70. But a 0 of order 70 looks very much like a step function. So to all intents and purposes, this is a uniform phase with then an exponentially increasing wall which takes you to the original phase.
Okay. So if I had just 2 vortices,
yes.
Wherever I put them, I get the same 0 energy?
In the absence of a trap, wherever you put them, you get the same 0 energy. In the presence of a trap, they get forced to lie on top of each other and form this big vortex. Okay, so here's the key idea. What's sitting in the middle here is the quantum Hall phase. Vortices are either fermions or bosons in the quantum theory, depending on whether K is even or odd. So at the moment, just think classically, and we'll quantize everything later. The whole talk is about how to quantize. We'll see everything as we go along. At the moment, as a classical statement, it's just true of these classical field configurations, that it's uniform.
You said this trapping potential is different from the one you get by the proportional.
Yeah.
What's special? What's select out this potential for you?
Oh, it was consistent with supersymmetry.
But the one you get by supersymmetry.
No, the one you get from conformal transformation is consistent with supersymmetry, which is some combination of supercharge plus superconformal charge. And I don't have the superconformal charge here. So it's because it's going on around mu. Yeah, it's mu.
You need the number of vortices to be large for...
It's going to be macroscopic. How many electrons are there in a typical quantum Hall system? 10 to the 11, 10 to the 9? Yeah, that's how many vortices I'm going to have. Okay.
So if the stuff where the vortices make is supposed to be your quantum Hall,
yeah.
Then the fact that the vortices are fine-tuned to not interact at all with each other, isn't that sort of very far away from modeling?
Do you know what okay, I've only been learning quantum Hall physics recently, and all these basic things said, yeah, it's the Coulomb force, it's the repulsions between these things which are responsible for the quantum Hall fluid. But then you look at these model Hamiltonians that have these ultra-local interactions, and there's no forces, right? The forces are delta function-like things. So it can't quite be true that it's those long-range forces that are responsible. And this, I think, is a very clean example where you can just calculate everything. It's not the long-range forces that are doing it. So here the gap is actually coming just from the presence of the trap. But you're still going to get the quantum Hall phase. The force is kind of the classical, well, at this level, the forces are just the classical fact that these aren't point particles. These are extended particles, and they...
I'll ask a question differently. So what determines the size scale of that? So I would have thought there's a trapping potential length scale, and then there's a length scale associated with the force between these, and they'll match up, and then you'll get a length scale of this problem.
So here's the nice... The trap was chosen specially so that the solution where all the vortices sit on top of each other, in the absence of a trap, remains a solution in the presence of the trap. That's really exactly the same solution. That's really what's special about this trap. So the trap doesn't determine the size of this, but the trap does determine the energy excitations above this. So the strength of the trap is called omega, and we'll see explicitly where it appears, but it doesn't determine the size. Okay, so let me just give you a heuristic argument. So as I said, the key idea is that inside here we have a quantum Hall fluid, and we can understand this quantum Hall fluid from various ways, either by looking at the classical effective theory, or by going and looking at the microscopic description of vortices and quantizing them and seeing their wave functions. So that's the basic idea. So just a very quick heuristic argument. You've got an external magnetic field. So if you just do the kind of usual Landau level quantization, the number of states that you expect per unit area is proportional to the magnetic field. The area of this classical vortex is given by this. So roughly speaking, if you divide the number of states by the number of vortices that you've got in an area, you find that you've got a filling fraction 1 over k. So already on this very heuristic level, you see that this is a quantum Hall state at 1 over k. But we'll see it much more accurately later. Okay, so this is the plan of the talk. It's to take this simple system and look at what's happening here in various ways. We'll look at the effective description, long wavelength. It's just a Chern-Simons theory built in. But we'll also look at the microscopic description of vortices. We'll quantize these vortices. We'll see that you get a Loftlin-type wave function. We'll be able to work with that wave function. We'll show that they have fractional charges and statistics. You can show that the edge modes are a chiral boson, which spins around. And all these different features of the quantum Hall effect you can see directly in this one picture. Okay. So that's where we're going for the rest of the talk. Any questions about this? All right.
The fact that it incompressibly comes from...
At the moment, it just came from the classical solutions of solitons, that you don't get to squeeze solitons together. When you squeeze them together, they form a big incompressible disk. And at a quantum level, we'll just do the calculation and see. Yeah. It's weird. You would think you...
Most of these things follow 1%.
No, the first thing follows from the Chern-Simons theory. These do not. The fact that it's a Loftlin wave function doesn't.
The exact form.
Yeah. Well, we'll see exactly what it is. It differs slightly, as I mentioned earlier. But the edge physics follows from the Chern-Simons theory. But so yes, but we'll see. We'll see. And it's really, the key point is really to link these microscopic descriptions and this effective description. The thing that I find slightly odd is you would think the right way to go was to start with a microscopic description and derive the effective long wavelength description. And here I've kind of gone the other way around. I've started from the effective long wavelength description, but by quantizing these vortices, you get back the microscopic physics. Okay, so as Senthil pointed out, the first of these is completely trivial. It's just what people wrote down 25 years ago. Outside the vortex, this was the vacuum. But inside the vortex in this big droplet, phi squared goes to 0, and B, which remember is not the external magnetic field, it's not electromagnetism, it's this Chern-Simons field, it's given by the following. And it means that inside the vortex you have an unbroken U1. So you've just got a usual Chern-Simons theory at level K, which is precisely the effective description of quantum Hall physics. But only inside, not outside. So you know you're going to get a Hall conductivity that's proportional to 1 over K. Okay? So the non-trivial stuff is trying to understand the quantum dynamics of what's going on here and quantizing these vortices. Okay, so I need to tell you, this is the goal of the next few slides. The goal is to write down the Hamiltonian that describes n interacting vortices. And then we're just going to go and solve it. The Hamiltonian is very easy to state. It's very simple, but it's not of a form that's probably that familiar to condensed matter physicists. Okay? So what I want to do is try and motivate this form. I'm not going to derive it in full detail, but I'm going to try and motivate where this form comes from, and then I'll give it to you, and then I'll explain what the Hamiltonian is and what you can do with it. Okay? So here's the basic idea. I said already, if you solve these equations for n vortices, you don't have a unique solution, but you have a solution with 2 n parameters, because the vortices can sit anywhere. Okay? So there's something that we call a moduli space. I have a feeling this isn't familiar in condensed matter, because I sent this paper to PRB, and the referee said, this is really good, but you need to define what a moduli space is. So let me tell you what a moduli space is. It's really simple. It's just the space of solutions to these equations. Okay? So these equations have 2 n parameters that determine the positions of these n vortices, and the moduli space is a big manifold of dimension 2n, and where you sit on that manifold specifies which particular solution you have. Okay? That's a moduli space. So it's a big space of dimension 2n. Good. All right. Sorry?
Why is it 2n and not n?
They're real dimensions. It's because they can move on the plane. Okay, so in the absence of the harmonic trap, you have this moduli space of vortices, just a space of classical solutions. Now, what we want to do is write down the quantum mechanics that captures these 2n degrees of freedom. Okay? Describes what's going on. So let me back up a little bit and tell you about a related system. If I'd written down an abelian Higgs model, you guys are good? Yeah? If I'd written down an abelian Higgs model rather than a Chern-Simons model and tuned it between type 1 and type 2 superconductors, I'd have exactly the same vortices and exactly the same moduli space of solutions. Okay? Sachin? That's right. It doesn't have a boundary. No, we're going to forget about the trap for now. We're going to put it on later. So the moduli space of a single vortex is just R2 because it can sit anywhere on the plane. Yeah, and the moduli space of 2 vortices is topologically R2 times R2 mod Z2 because they're indistinguishable. It actually looks like a cone times R2.
For the pictures that you do where you have a single large droplet of 70 vortices, you have a exponentially rising...
But that's a particular point in the moduli space. That's the point on the moduli space where all the vortices sit on top of each other. Yeah, the rising is to do with the profile of the vortex, the solution itself. Okay. So suppose that we were in an abelian Higgs model. Now we have these n vortices, and they can move around, and these positions of the vortices, the 2n parameters, simply parameterize the configuration space of vortices. So the thing I've called the moduli space in that case is just the configuration space of vortices. So there's an old idea due to Nick Manton that in this case there's an action that governs the vortices which just takes this sigma model-like form. So the x capital A's are coordinates on the configuration space. And there's some metric that you can write here. And this is just the dynamics of the vortices. Okay? There's some nice physics in here. You know, the vortices, if you just put them there, don't do anything. But if you make them move, they have very interesting scattering. You get, for example, right-angled scattering and things like this. So the idea is that this metric is constructed, and there's a formula for it, in exactly the right way. So geodesics on this moduli space capture the dynamics of these solitons as they move. So this metric has been studied for many years, starting in the early 1980s. It's not known exactly for all vortices, but many of its properties are known and understood. Okay, that's for the abelian Higgs model. For our model, the dynamics is first order, not second order, which means this same object, the same moduli space, is the phase space of vortices, not the configuration space. So the kind of dynamics you expect is not second order dynamics, but some first order dynamics where now there's some function, or in fact 2n functions of x here. And this function was understood and computed, well, sort of Nick did it in 97, but in a very sort of arcane way, and then Nuno Ramau and Martin Spate about 10 years ago. It's known that this function is related to the metric that I showed you earlier. So this requires a bit of geometry, and if you don't know it, I won't try and explain. But you know, if you know a bit of geometry, then d of f is equal to omega, where omega is the Kähler form for the previous metric. It's a different problem, but it was a supersymmetric abelian Higgs model. So it was a different problem, but the same kind of geometric object appears. So it's quite nice. Okay, so this is the kind. Because the action is first order. So the momentum conjugate to phi is phi dagger, basically. Okay, so this is the form of the action. There's some functions here that we need to understand. Again, a lot is known about these, but the explicit forms are not known. And, sorry? No, it's smooth everywhere. It's Kähler, of course, has various other properties, but it's not singular. Yeah, but you think, sorry, by the identification? Yeah, but things are nice and smooth. So, you know, when two vortices come on top of each other, which is where you think you would get the singularity, they just become this nice big droplet. So said another way, C cross C mod Z2 becomes a cone, a nice smooth cone, cross C. So where you thought there might be a singular point on the cone, it gets smoothened off. Okay, finally, we need to know about the potential, and the potential, it turns out, is just equal to the angular momentum of the vortices. So the action that we want at the end of the day is something of this form, where the xa's are the 2n degrees of freedom that tell us about the vortices. There's some functions here, which tell you about, well, basically really the symplectic form on the moduli space, and then there's some potential here. So we sort of know officially what these functions should be. The trouble is there's no explicit form for them. It's just not known for multiple vortices. It's a hard problem, and it's never been solved. So now comes the point where I sort of pull something out the bag. Some years ago, Ami Hanani and I looked at this problem, but using string theory and using D-branes. And we showed that there's a completely different description of the vortex moduli space, which is much more tractable and is going to be the description that we work with. So for string theorists in the audience, the analogy is if you take instantons in Yang-Mills theory, there's the ADHM construction for the instanton moduli space. There's exactly the same thing for vortices, where if you want to study vortices in gauge theories, there's a similar quotient type construction for the vortex moduli space.
Sorry, so in the previous slide, when you had the unconventional harmonic graph, you're considering unconventional omega is very small, right? Because the previous exponential algorithm had already taken the velocity for the velocity of the motion.
Do you know what? There's something amazing here. In this case, you need the low energy limit. In this case, it's exact. You don't need a low energy limit. It really surprised us. Yeah. Okay, so let me tell you what this new description of the vortex moduli space is. So remember, the thing we're trying to describe is this 2n dimensional manifold, which is the phase space of vortices. G.
It's exact too, because it's non-relativistic.
Yes, yeah, it's exact with the potential. And I think the real reason is that the dynamics is determined by a conserved charge. You should think of now angular momentum as the Hamiltonian. And so it's exact. But yeah, physically, you're right. The reason the vortices have to be slow is because in the abelian Higgs model is you don't want radiation rippling off. But here there's no radiation. So. Okay, so here's the thing I'm going to pull out of my hat. Here's the new description of the vortex moduli space. And it sounds a bit odd. You take an n by n complex matrix Z. Okay? And then you take an n-dimensional vector phi, and you insist that Z and phi obey the following equation. So Z commutator Z dagger plus phi dagger. So this is an n by n matrix. Phi is a vector, but I've not put them together to do phi dagger phi. I've put them back to back, so phi dagger is also an n by n matrix, is equal to the unit matrix with the integer k that sits here. So k and mu were the parameters of the Hamiltonian, and z and phi are the new things I've introduced. If you can find all the solutions to this equation, and then you identify solutions that are related by the following un gauge transformation. Z transforms in the adjoint, and phi transforms in the fundamental. The solutions to these set of equations are exactly the moduli space of vortices. Okay? So this was something we showed using D-branes. If you know a bit of string theory, it's very familiar to have positions of n objects captured in an n by n matrix like this. But this is the description of the vortex moduli space we can work with. Okay, this is where I was really worried I'd just be losing all condensed matter people. So let me tell you the final Hamiltonian for vortices, and then take questions. I'll take questions now.
Yeah, so how the x is related to...
Good.
Given the solution, how do I identify?
That's complicated in general. Let's just do some simple counting. There's n squared degrees of freedom in here, but they're complex, so there's 2n squared. And there's 2n degrees of freedom in here. This is a real matrix equation, so there's n squared constraints, and I divide by un, which has n squared elements. So it's 2n squared plus 2n minus n squared minus n. So at least the number of solutions to this should be 2n, which is right. If the vortices are far separated, roughly speaking, the eigenvalues of Z then becomes almost a diagonal matrix, and the eigenvalues of Z become the positions of the vortices on the complex plane. Okay? The other case we understand is when all the vortices sit on top of each other and you get the big droplet, and then there's just a particular solution of these equations which corresponds to that. But in general, it's a complicated map. So we understand the map in some places, but not in others.
So when they are well separated, what is the role of phi?
Roughly to turn off the slight off-diagonal elements of Z. Okay, so this finally is the action which governs n vortices. It's a quantum mechanics, but it's a quantum mechanics that for n vortices has a un gauge symmetry. Okay, so it's slightly odd. And there's an n by n matrix Z, which is minimally coupled under this quantum mechanical gauge symmetry and transforms in the adjoint representation. And then there's a vector phi, which transforms in the fundamental representation. And then I turn on this Chern-Simons-like term for quantum mechanics, and then I add this particular potential, which is capturing the harmonic trap. Okay, you can see it's Z dagger Z, so it doesn't want things to move away from the origin. If you look at Gauss's law for this, Gauss's law is exactly this constraint that I wrote on the previous slide. So this is the Hamiltonian for the action describing n microscopic vortices. It's slightly different form from what you were probably expecting, but this is the thing that we can work with and solve.
So what's little a0?
Little a0 is a gauge field in quantum mechanics, and it's a un gauge field.
So here the covariant time derivative has small a0 in it.
Small a0 in both, yes.
Physically, the eigenvalues of Z are the positions of the vortices, right?
Yes, yeah. Certainly when vortices are well separated, that's the right interpretation. Phi is, it's some sort of auxiliary field that at least in this context, doesn't really have an interpretation. It just allows you to solve this equation. But it's the eigenvalues of Z, I think, that you should think of as the important.
Where is the information about the quantum statistics of the vortices?
We'll see. It'll all come out, yeah. We've just got to quantize this, and we'll see. Yeah, I've not put any quantum mechanics in yet, right? I've just looked at the classical dynamics of vortices, and this is the thing that governs their action.
This is the exact theory, or somehow because it's integrating out everything above the gap, and or
Integrating out everything.
right.
Yeah, yeah. The gap is of order mu, and I'm certainly at energy scales below mu. Yeah, there could easily be 1 over mu
Sure,
corrections.
this is fine, but I'm just curious as to whether this is completely exact or is it only
No, it's 1 over mu for sure. Yeah. Okay, so this is the dynamics of vortices. Yeah.
So there is a gap,
Mm.
and so we are ignoring all these degrees of freedom. So then the size of the harmonic trap has to do with something to do with that gap.
I see. So that's right. We're going to look at excitations of these, and you want to make sure the excitations, which are determined by omega, are not going to be, but they're parametrically separated. The gap is mu, the harmonic trap is omega.
So there is some relation between. I mean.
No, there's no relationship between them, so I can always make mu large and omega small and always be safe.
But at the edge of your droplet, you go, there's no omega.
Yeah.
But the phi becomes 0.
Phi becomes mu outside, yeah, but you're still in the 0 energy state. Yeah, you're not exciting these. Yeah. Oh. Okay, I'm. Can't produce fermions. We'll see them actually. We'll see them coming out. Okay, the last thing I want to say is that we were the first people to realize this was the description of vortices, but we're not the first people to write down this action. This action was written down 15 years ago by Alexios Polykrinakos. He called it the quantum Hole matrix model, and he wrote it down as not really sure where he got it from, through lots of intuition about Calogero-Moser models and various integrable systems, but he wrote this down and said, this should capture the dynamics of the fractional quantum Hole effect. And there were then a flurry of papers explaining that it did indeed capture various bits of the fractional quantum Hole physics. I'll review those papers, or review the important results, and then we'll go much further and show that we can do much more with this than was done 15 years ago. Okay, are there any questions about this action? From now on, if you like, you can forget everything I've said before, and you can just start from this action. The last hour has just been trying to derive this action. Okay. I didn't hear the what? No, this is in LaTeX var phi. Looks similar? It's different. Yeah, it's got nothing to do with the three-dimensional bosonic field. This is just a vector in quantum mechanics. No, we can't read off the solutions to the vortex equations from this. Just capturing the moduli space. Yeah.
I don't understand how, I mean, I guess you explained that the eigenvalues would be represented in the vortices more properly. But let's say I'll ask about some physical operator. So the density operator of these vortices. Is that the GZ dagger?
No, that.
And that's a matrix in the Landau level.
You know, this is the trace of Z dagger, Z dagger Z.
So that's the density.
That's the angular momentum of the vortices. I think the density is hard to get from. And you can always just look where the eigenvalues are and then from that extract the density. See, part of the problem is that when the vortices are well separated, they have a well-defined position. So you know how you should label them. As they come close, they kind of lose their identities, right? We've seen that one vortex.
But when you think about the density operator, that's very fine.
Yeah.
But, so you're saying it's not related in any simple way to, well, it's obviously gauge way.
The trouble is there's not many operators you can write down in this because you have this gauge symmetry. So there's only a few. There was a paper back in the early days of this by Hansen, Carl Heder, someone else, trying to answer exactly this question. So they have a candidate for the density, but it was not simple.
Sorry, so lost a little bit. The spatial information about these vortices. Earlier, each vortex had a position, and that's somehow buried in the matrix index of Z, or what?
It's roughly speaking, the position is the eigenvalues of this n by n matrix.
Okay.
Where would be the off-diagonal matrix?
They don't really have a simple interpretation. No, they have a lovely interpretation in string theory, but I probably best not go there. But in terms of simple physics, I don't think there's a simple.
How do you have separated time and space?
It's just, you know, this is telling you, well, the spatial positions are captured in Z, and this action is telling you how they change in time.
The objects that sit in the matrix, space and time.
Oh, no, they just depend on time. They're like the positions of the vortices. So yeah, Z and phi only depend on time. Okay. So what should we do with this? The goal is now to quantize this action. Why a large n limit? I'm going to be at finite n all the way through, but. Yeah, we can just solve it, as we'll see. Okay, so let's see how you quantize this. Firstly, just canonical quantization equations. The dual of the momentum conjugate to Z is Z dagger. Momentum conjugate to phi is phi dagger, because they were first order in time. So the commutation relations are just Z dagger is identity, and phi dagger is identity, where these are the UN indices. So A and B run from 1 to n. So these are just creation and annihilation operators. You introduce a vacuum 0, and the vacuum is annihilated by Z and phi, and you build the Hilbert space by acting with Z dagger and phi dagger. Okay, so very simple. All of the subtleties come from the fact that there's a gauging. And in particular, Gauss's law for this gauging is this constraint equation that we looked at earlier. So all the physical states have to obey this viewed as an operator equation acting on states. Okay? So it's best to split this UN equation into an SUN part and the trace part, which is the U1 part. The SUN part of Gauss's law is simply telling you that all physical states should be singlets under SUN gauge transformations. The U1 part comes from taking the trace of this, and because there was a Chern-Simons-like term here in a quantum mechanics sense, this disappears because you take the trace and it's a commutator. This turns into the number of phi, so that's phi dagger phi, and this should just be equal to k times n, and the n comes because I've taken the trace of this. And there's a slight normal ordering shift, k goes to k minus 1. This follows from turning phi dagger into phi dagger. Okay? So these are the physical states. They're SUN singlets where you have exactly this number of phi excitations. So very straightforward. Finally, the energy, well, you pay an energy cost whenever you excite a Z. Okay? So that...
You don't have any combinator between Z and phi?
No. We'll see how they interact. They interact in a lovely way, but we'll see just now.
Hilbert space, gauge being physical Hilbert
Yes.
space. This isomorphic, the Hilbert space below the other level.
We'll see. We'll see. This is exactly what we're doing. Yeah. So this is the game. You've got the state 0. State 0 is not a physical state because it doesn't have any phi dagger excitations. So you have to act on the state 0 with this number of phi dagger excitations. You can also put Z excitations, and it only costs you energy if you put Z excitations. But the whole thing has to be an SUN singlet. So how do you do it? The point is that you've only got phi daggers to act with. You can't act with phis, which are the fundamentals, because they annihilate the vacuum, or the state 0. So you've got to act with the phi daggers. But if you want to build a gauge invariant operator out of phi daggers, these are anti-fundamentals, there's only one way to do it, which is what a high-energy physicist would call a baryon. Or in other words, having an epsilon symbol and then lots of phi daggers. So the only way to build a gauge invariant state is, let's just look at what's in brackets here, is to have an epsilon symbol going from A1 to AN, and then n insertions of these phi daggers. The trouble is that the phi daggers are bosonic. They commute with each other. So if you just had an epsilon with a whole string of phi daggers, you would anti-symmetrize and you would just get 0. So the only way not to get 0 is that you put the first one as phi dagger, the next one has to have some z dressing it, and the next one has to have some other power of z dressing it, and so on and so on. But you pay energy costs for z. So if you want the lowest energy state, you put a phi dagger here, the next one you put a phi with a z on it, the next one a phi with a z squared, and so on until the last phi has a z to the power n minus 1. And this whole object in brackets is the gauge invariant operator that you get to act with. So you see that there's this nice interplay. You only get energy costs for z, but the gauge invariance is telling you that the z's have to be sort of related to the phis, which are obliged to turn on in some interesting way. And so the gauge symmetry sort of builds up these states that will end up being very highly entangled. Okay, so that's the essence of what this quantum mechanics is doing. So at level, well, this is the simplest gauge invariant operator. It's what we would call a baryon operator. And the ground state at level k is to act precisely with k minus 1 of these operators on the state 0. Okay. Excited states, you want to know the Hilbert space. Excited states, you just put z's here, and the z's all have different powers of their exponents. So
understand the thing powers of z dagger, I understand that you need to stick in some z's to make to construct something that's capable of being anti-symmetric. But where do you need powers of z dagger?
because it's the only thing you can do to make the entry for A1 different from the entry for A2, and then different from the entry for A3. They've all got to be different from each other. So the general one is epsilon A1 to AN. You can put a Z to the R1 phi dagger A1, Z to the R2 phi dagger A2, all the way up. So you anti-symmetrize between everything, but all the R's have to be different from each other. And you pay energy costs for Z, so the lowest energy state is this is 0, this is 1, this is 2, this is n minus 1. Okay. So you build up these interesting Hilbert spaces.
So the energy of this is something like k minus 1 into n minus 1.
K minus 1 into...
Your omega times me.
I think that's right. This doesn't have zero energy in the quantum theory. Yeah. Yes, that's exactly right. Okay, so this is the ground state of the system. This is very, very similar to the Laughlin wave function. So here's the Laughlin wave function, the ground state for the filling fraction k. It's usually written in this nice form. But this kind of van der Monde determinant here, you can write in the following way. There's an epsilon symbol. You have z to the a1 to the power 0, z to the a2 to the power 1, all the way up to z to the last one to the power n minus 1. So this factor here is just another way of writing the van der Monde determinant. In fact, so it looks like a determinant. This looks very, very similar to this. It's exactly the same structure, but the symbols mean different things. So here, the symbols, of course, are the positions of the electrons, which people have been stressing is not obvious in here. Here, the Zs are these operators. So similar structure, but we need to somehow, if we want to compare this to this, we need a way to do exactly what people have been asking me. How do you extract the positions of the electrons from this wave function? And so the simplest way to do it, this was done in a lovely paper by Karabali and Sakita, is just as I was said, take the eigenvalues of Z. Or said another way, take Z and diagonalize it as a matrix and read off those diagonal elements. You can diagonalize Z. You can't diagonalize Z dagger at the same time, but you can diagonalize Z. So if you do that, you get a wave function written in terms of coordinates. They showed the following. They showed that the zero state, which holds when k is equal to 1, is precisely equal to the Laughlin wave function, which of course is just a fully filled Landau level in that case. Meanwhile, the states when k is greater than 1 are almost the Laughlin wave function. So they're equal to the Laughlin wave functions at large distances when the separations between all particles are large, but they differ as these particles come close to each other. And in particular, this wave function doesn't have a 0 of order k as two particles come on top. It has a much softer zero than the Loftin wave function. Okay? So if you read this paper, they're kind of upset by this. You know, they're worried that, you know, they've got the wrong wave function and somehow they have to change their matrix model, or maybe they have to change the map because they really want the Loftin wave function to come out. And I think it's absolutely the wrong strategy, because there's nothing special about the Loftin wave function. This is equally as good, and as I said earlier, it's better. It's better in the sense that it's much easier to work with this because it's some kind of coherent state representation of the Loftin wave function, and we can calculate with it much better. Okay, any questions about this? Yes. It follows from this epsilon symbol. So whenever you have an SUN gauge symmetry, there's always as I said, what we call a baryon, but there's always a way to write down an epsilon symbol and then contract fundamental things with it, and that's always invariant. If you transform, it's invariant under SUN. If you transform this under an SUN transformation, you'll see it changes by a determinant of that group element. But by definition, a determinant of an SUN group element is 1. That's really what's going on. Yeah?
Can you just repeat the connection between little z's and the what?
Yeah, so write diagonalize z, and the diagonal elements, you then, so these are still operators, but you look at, think of these states as eigenstates of these operators, and then you get from operators to numbers.
You need the x on the left and the x on the right different perhaps because there is a complex
No, I think they're not unitary, but you can have x minus 1x.
These substitutes are what? They're unitary.
No.
But they have complex eigenvalues.
Oh.
These z's are
Yeah.
then you need the
Maybe that's right. Maybe it's u and v.
on the right way.
Maybe it's u and v. Yeah. Sorry, you're right. So it's, good. Do the same. It's not a unitary x, though. That's important. Yeah. Okay, I'll brush up on first-year mathematical vectors after the talk. Okay, so these are the new wave functions that we have. So they're coherent state representations of the Loftin wave function. There's a story about edge excitations, but that's kind of boring. I just sort of want to move on. Yeah.
So these were the zonic, I don't know what that means. So if I were to represent a quote-unquote state of electrons, even denominator this formulation doesn't change in phase.
Remember that the vortices that we had in the original theory were themselves fermions for odd k and bosons for even k. And now we've quantized them, and we've got wave functions that make precise sense. These are wave functions for.
This is the logical starting point. Forget about anything else. Say, okay, you have some interesting representation of wave.
How would you have known that these were bosons or fermions? Is that the question?
Yeah, I mean, by explicit construction, it seems as though for the even k, there's a symmetric wave function.
Yeah, absolutely. Yeah. That's right, because they were bosons for even k and fermions for odd k. The original vortices. Yeah. Okay, let me tell you about the quasi-Hole excitations. I should say that no one's managed to figure out how to write down wave functions for quasi-particles in this matrix model. In fact, I think it's clear the matrix model doesn't include quasi-particle excitations. I think you have to add something like a Wilson line in the original theory. So there should be some deformation of it that does include quasi-particles. But it has quasi-holes. And one of the things we did was figure out what the wave function corresponding to quasi-holes is. And it's very simple. You take this ground state, and you act with a determinant operator. So Z is an n by n matrix. Eta is just a number that tells you the position on the complex plane of the quasi-hole that you're going to insert. And the claim is that if you act with this operator here, this gives you a quasi-hole state. Or if you want a state with lots of quasi-holes, I've got m of them here, you just act with lots of these operators. Okay? So one simple check of this is you do the same thing we did previously. You do the map from operators to the z's. You'll see that at large distances, this state here precisely agrees with the Laughlin state for a single quasi-hole. Okay. But now we can do the things that are hard to do with the Laughlin states. So let me, for those of you who aren't quantum Hall experts, let me review for you the ideas of this lovely paper by Aravash, Schrieffer, and Wilczek from 30 years ago. So here's the idea. Take a quasi-hole, which is a particular state with a quasi-hole at some fixed position, and adiabatically move that quasi-hole in a big circle in your quantum Hall fluid. Okay. So when you do that, your wave function picks up a Berry phase, which is given by the following transformation. So eta is just a parameter of the state. I write eta in polar coordinates. So what I'm doing is taking this quasi-hole and just moving it in a big circle around. Okay? So I compute some Berry phase for this ground state wave function. Now I think physically, what should this Berry phase be doing? Well, if this quasi-hole has some particular charge Q, then when it moves around in a circle, there's some magnetic flux in the middle there, and it should be picking up some Aronoff-Bohm type phase. And the Aronoff-Bohm type phase it should be picking up is the flux that it encloses times the charge of that quasi-hole, which is equal to, well, this is the flux that it encloses, and in terms of the variables of my theory, the external magnetic field was related to mu. So the idea is that you compute this Berry phase, you then compare it to this expectation, and by comparing this to this, you can read off the charge of this excitation, okay, the electric charge of this excitation. So this is the lovely idea of Aravash, Schrieffer, and Wilczek to show that these are fractionally charged and fractional statistics. But as I said before, you can't do this calculation for the Laughlin wave functions, because you can't do this overlap. They needed the plasma analogy in order to do this, and the assumption that these were uniform states, which you only have through the plasma analogy.
I mean, uniform state you can get in many other ways.
Only using the plasma analogy.
Not really. I mean, you can put this wave function on a sphere, and you can show that it has zero angular momentum, which tells you that it's rotationally invariant. So as far as I can understand, it's not clear to me where plasma analogy. So uniformity was used, but plasma analogy is not the only way to get that.
I see. It could be certainly in their paper they use plasma analogies, and certainly in these subsequent papers by Nyack and Bonderson and people who were trying to do similar things for non-abelian states. Their motivation, well, the reason they found it difficult was because they didn't have the plasma analogies that Aravash and Schrieffer and Wilczek had. I see. I believe what you're saying, though, that there are other ways to do it. There's nothing wrong with the plasma analogy. It's just,
I'm saying that this calculation can be done exactly for Laughlin spaces. You don't need that.
It wasn't done in the original paper exactly. And you just can't do the integrals to get this buried. Let me show you the results, and then we'll come back and see, because they're just on the next slide. Okay, so the nice thing, yeah.
Does the state eta k begin with? Are there many states with the same energy?
The energy of the system doesn't depend on eta.
The one that you're the one that you're parallel transport. Is that a non-degenerate state, or is it?
Oh, I see. And it's the energy doesn't change as you vary eta. So in that sense, it's degenerate, but that's precisely what we're changing.
Maybe let me just ask my question, because whether the state is degenerate or not, the Berry phase is a U1 phase or a UN phase.
Oh, it's not a UN Berry connection, of course.
So
Yeah.
So that's what I wanted to know.
Yeah, it's just a U1 Berry.
In that sense, it's a non-degenerate.
It's not mixing with other states. That's right. Do you know what? If you have to make eta changes, eta times e to the I omega t, which means that this quasi-hole actually naturally processes in the trap, and then it's an energy eigenstate. Okay, so I still claim that you can do this calculation in a way that you can't do the Loftin wave functions, but I'll tell you what I mean by this. So actually, let me go back before I get to the scary formula. This is the state we want to compute the Berry phase of. And as we saw, the ground has all of these z daggers. So the ground state's quite difficult in terms of operators. But these operators, we know the commutations between them, which means it is possible to compute the overlap of this function. It's not easy, I should say. And I should also say that this calculation was done by my student, Carl Turner, who's completely amazing, and just sat down with this huge book by Mahon on symmetric polynomials for about a month until he could nail this calculation. But it was really quite impressive what he did. The analytic calculation you find is that the Berry phase, as this thing moves around, is given by this horrible combination of hypergeometric functions. So this is for an arbitrary n number of particles and an arbitrary k filling fraction. I claim this is the answer that you can't get for the Loftin states. You just can't do those integrals to get the exact. Of course, you might not care about that, but I think it's what you can't do. So this is the function. It looks horrible, of course. Here we've just plotted the function compared to this dotted line which is underneath, which is the expectation from a particle moving around and just picking up the Aronoff-Bohm effect. So this is the R squared potential. So you see it matches perfectly the expectation from an Aronoff-Bohm phase, and then at some point it turns around and flattens out. This is because we had a finite number of electrons, and this is just the edge. So this is where the hole has been moved outside of the quantum Hall droplet, and so the Berry phase just flattens out. So we get this exact answer for a finite number of electrons, including edge effects that appear here. Oh, that's a good question. I think it's in thousands. Yeah, although thousands of what, I can't remember. Yeah. Okay, there's a related calculation. Again, also in Aravis, Schrieffer and Wilczek. Now you put in two quasi-holes. Yes, please. Yeah.
So I'm just trying to understand what exactly is being done here.
Mm-hmm.
So the R is the radius on which you're moving that.
R is the radius of this from the origin.
Yeah.
And theta was the thing the Berry phase we were computing.
And this 50 to 60 where it starts flattening out.
Yes.
That is the radius of that.
That's where this red dot hits the edge of this droplet.
Right.
Yes.
So after that, there's no quantum Hall.
Good.
Right?
So what's happening here is that this is a coherent state representation. So the state for one eta is not orthogonal to a state for another eta. And so what happens is when eta hits the end of the Hall droplet, basically all of these states degenerate. So the state you're computing the Berry phase for here, is essentially the same as the state you're computing the Berry phase for here. Yeah, it's just eta becomes a bad parameter to label these states. Okay, the next calculation is to compute the statistics, again, just following the path laid down by Aravis, Schrieffer, and Wilczek. You put in two quasi-holes, one in the origin, the other one you move around. You compute, again, the Berry phase as you move this one around this one, and this tells you the extra statistical phase that you pick up from this quasi-hole. Again, it's quite a long calculation, but it's possible to compute these overlaps explicitly. You get another, even more horrible expression for the phase. These are now confluent hypergeometric functions. They have a twiddle on top, according to Mathematica. And this is the statistical angle that this one picks up as you go around there. Again, there are edge effects. If this gets too close to the one in the middle, there's a bump. And then there's a long plateau. This was plotted for, I think this was plotted for 5,000 electrons, 5,000 vortices at filling fraction a third. And you can see that the statistical phase is exactly what, you know it has to be from usual Loftin arguments. But I think with some extra precision in here that I might be wrong, has not been done for Loftin wave functions.
So what is that scale that over which it deviates? What is that length scale?
That's a good question. It must be the size of the vortex, which is 1 over mu, basically, with a k in there as well. But I think mu is the dimensional parameter that's setting that.
How about when it's a magnetic?
Mu is the external magnetic field, so yeah, it's the same thing. Yeah, although I haven't looked carefully. Yeah, the fact it's a 20, if that's an interesting question, I can certainly extract it from this. You see, I think it's quite nice you get edge effects, but I don't know what to do with it, and I don't really know if this is something that's interesting to you guys or not. It's exactly what I'd like to hear from this talk. Okay, that's the end of the abelian Hall story. So there's more to say about the non-abelian story, where I think things get more interesting. But this might be a good time to pause, take questions, take a break, or whatever people feel like. Sentil.
So the top point, tell me if I'm wrong, I'm probably wrong, but tell me why I'm wrong. So couldn't I have started this entire talk from the place where your matrix model appears?
Absolutely. Yeah.
And just run it forward?
Yeah, 15 years ago, people did that. But part of this was to understand how that matrix model was connected to more general low-energy effective physics, like the Chern-Simons theory.
So on that, somebody, maybe that person, guessed the matrix model for some reason.
Polychronakos, yeah.
And then said that you can construct, can represent the Hilbert space of the physical Landau level in terms of these.
And he could have done this calculation back then.
Right, okay. So that made him, how did he guess that model?
I don't really know. You know, he was an expert in Calogero-Moser, which has some connections to. This is this integrable system in one dimension, which has some connections to Landau level physics. And then Susskind came up with this non-commutative Chern-Simons description of quantum Hall physics, and Polychronakos was somehow inspired by that. He thought this was related to that. I think it's related. It is related, but not quite in the way they thought back then. I'm not sure. He's a smart guy, Alexis.
So I missed the part where the Hilbert space of this matrix model was the same as the lowest Landau.
Oh, I'm not sure. Yeah. So this is the Hilbert space of the matrix model. It's all functions of this form.
That z bar phi equals 0, so they are all the anti-holomorphic.
Yeah, on that naive level, there's z's in here, but no z daggers. So in some sense, yes.
Another connection that showed is that the Gauss law coming from that matrix model is the same as the ABA calculations which describe the instantons of the Chern-Simons. The instant on the vortices. So yeah, but I mean, when one says lowest Landau level, it's much more of a statement about that type of state.
So let's say K is even, let's say. Yeah. So it's a boson system. Then of course, these states apparently are symmetric holomorphic solvents.
Yeah, that's right. Yeah. So under this map, that's exactly right.
How about the Gaussian?
Oh, the Gaussian is buried in this, actually. This was a coherent state representation. And so, the ground state of a harmonic oscillator is the Gaussian. So you sort of get that for free. So it's sitting there.
Is that because you put things in a harmonic trap?
No, and even in the absence of a harmonic trap, that Gaussian would have been there.
So that, for example, the quantization relation is very like a bunch of A's and A daggers. So it is fair to say that the Hilbert is actually an infinite dimensional space. Space of, so that we see that ties up with this discussion about whether when you need a different X hat.
Oh, this one?
No, because the Z is actually
Z is an n by n matrix.
but a bunch of A's and bunch of A, and so you're looking at unitary transformation on this infinite dimension.
But the infinite comes from acting with lots of Zs. Each individual Z is just an n by n matrix.
Z is
It's true, but all the elements of Z commute with each other, so I think that's not relevant. All right, what do we think? Pause for a break? Okay. There's much less to say on the non-abelian stuff, so it'll be short. It's going to be much quicker because we haven't really done the work yet. We've done about a third of what's needed to give a decent talk on this subject. But what we have done, I think, is interesting, so I'll try and tell you about it. So the simple question is, can we do non-abelian Hall states? And everything I did was really always a warm-up to try and answer questions that people haven't yet answered in quantum Hall physics, and really looking at non-abelian states. And so the starting point was very simple. It was just we take a non-abelian Chern-Simons theory, and we're going to work with, it's maybe not quite the right notation. I may still change it in the paper, but n is already the particle number, so it can't be un, and k is the level, so it can't be uk. So we've chosen up. Okay, so it's a up Chern-Simons theory. It's named after a state in the north of India. So, so now we repeat everything that we did before. We start with this Chern-Simons theory. We look at vortices, which are now vortices in a non-abelian theory. We figure out their moduli space. We write down the matrix model for their moduli space. All of that I'm not going to bore you with. I'm going to do exactly what Senthil suggested I do. Just start with the description of the dynamics of these vortices. Yes? No, in fact, it's important that you have P or more species of fundamental matter. The reason is that you want to be in a phase that has vortices, but you only have vortices if the gauge group is completely broken. And every fundamental matter can Higgs UP to UP minus 1, and then the next one to UP minus 2. So you need at least P fundamental matters.
Previous abelian case, you only had one chiral molecule.
Yeah. No, I'll add them all in the fundamental representation.
I guess I'm thinking of having both of them in the entanglement.
You can do that, and you know something weird happens with the algebra in that case when you turn on this deformation mu that I haven't fully understood. So I won't talk about that. Okay, so what's the matrix model? The matrix model, it turns out, is extremely simple generalization of what we had before. This was the polyquinarchos theory that we looked at for the Laughlin state. Z is the n by n matrix. Phi is the n column vector. And all we do is we now introduce p copies of phi. So, sorry? Oh, I'm sorry. Yeah, we changed notation in the two papers, and I've cut and pasted. B is what I previously called mu. Sorry. So yeah, B is the external magnetic field. Yeah, sorry about that. And so now we've got p copies of these phi's. Other than that, it's exactly the same. And the constraint equation that comes from Gauss's law of this is ZZ dagger plus the sum over the p copies of the phi I dagger is equal to the identity. And so the question is, can we solve this matrix model? No, the SUP is a global symmetry, so there's only a UN gauge symmetry. I started with a UP gauge symmetry in 3 dimensions, but remember when you have solitons, they descend to global symmetries on the world volume of solitons. So for example, instantons have this UN rotational symmetry. So the same is true here. Okay, so all we have to do is solve this matrix model. Doesn't. No. Still the same as before. All right, so we have to solve it. If this were a finished project, this is what I would tell you. I would say these are the ground states written in terms of operators, kind of things that I was writing on the board here earlier. That we can do. That's very simple. And then I would say, and here's the map to the coordinates, the kind of thing that people have been discussing. And these are the quantum Hall wave functions that you all know and recognize, and you know exactly what kind of quantum Hall state this is. Okay, that's the story I would like to tell. I don't know how to do that. And it's turned out to be remarkably subtle, and we've not figured it out yet. I can tell you why it's subtle, but then I'll move on and tell you the stuff we have done. The reason is that each individual electron now, each individual vortex, has an internal spin degree of freedom. Okay? And the spin typically is not a spin half. So the spin, the number of internal states for each electron, depends on both p and on k. So there's some quantum Hall state for electrons that have rather high spins, and spins not just of SU2 but of SUP. Okay? So the closest I can find to these kind of states in the literature are called the non-Abelian spin singlet states, and they were written down by Schoutens and someone whose name I can't. Ardon, exactly. And so the kind of states we're getting are very similar to these non-Abelian spin singlet states, but I haven't quite managed to make this match correct yet. So that's the kind of quantum Hall states we have. All I can tell you is that all these electrons have spins. The ground state wave functions are spin singlets, and these ground state wave functions are by construction in the universality class of wave functions which come from SUP at level k. So they are the wave functions associated to SUP Chern-Simons at level k. Okay. I wish I could do more. I'm sorry I can't. By the way, a question. Do quantum Hall people know the ground state wave functions for SUP at level k? Is that something? I know that, for example, Moore Reed is supposed to be SU2 at level 2, which is odd, because here, the SU2 at level 2 is necessarily a wave function for particles with spin half. And the Moore Reed wave function is not a wave function for particles with spin half, it's a wave function for spin polarized states. So I'm not sure that it can quite be true that Moore Reed is. I think there can be some subtleties here, and it's exactly the kind of thing I'd like to iron out with this exact approach. I should say that the wave function we have for SU2 at level 2 is not Moore Reed, but if you project on something, it looks very much like Moore Reed. So it's definitely got some Moore Reed-esque physics in there. If you project in a different way, it looks like the 331 state, though. So So we haven't figured that out yet. We don't know exactly what the quantum Hall wave functions are. We know in operator language, but not in wave function language. All right, the next things we'd like to do is figure out things like edge dynamics and non-Abelian anyons. This is the thing we've been focusing on, and I think we've made remarkable progress. The reason we made progress, by the way, is because this is my fantastic student, Carl. This is my fantastic supervisor, Nick Dorey. I haven't worked. I was a PhD student in Swansea, which is in Wales, and then at the same time I got hired in Cambridge, my supervisor Nick also got hired in Cambridge. So we've been colleagues for 12 years now. We've not written a paper together for the last 15 years. But I was telling him and trying to get him excited about quantum Hall physics, and he knows all sorts of amazing maths that I could never dream of understanding, some of which I'll show you shortly. And he just solved this problem literally in a weekend. So it's really Nick that deserves most of the credit for what follows. So what can we do? This is a quantum Hall matrix model for some non-Abelian quantum Hall state. And we know from construction that this should describe SUP Chern-Simons at level k. So on general grounds, on the edge, there should be a conformal field theory, which is the Wess-Zumino-Witten model, SUP at level k. And so the question is, what can we find about that Wess-Zumino-Witten model from this quantum mechanics? And the answer, as I'm about to tell you, is almost everything. So let me explain what I mean by that. If there's a conformal field theory, which is a Wess-Zumino-Witten model, a Wess-Zumino-Witten model, for those who don't know, is a particular conformal field theory in 1+1 dimensions. The smoking gun, or at least one of them, is that it has an SUP global symmetry. But a symmetry in conformal field theories is a very powerful statement because it gives you what's called a current algebra in the operators of the conformal field theory, that there has to obey a very, very restrictive set of commutation relations. And the nice thing, and I should say that it was really Carl who figured this out, is that you can construct this current algebra explicitly within the matrix model. So you take these states in the matrix model with these operators in the matrix model with m greater than 0, and these operators in the matrix model sorry, I've sort of said this wrong. There should be a minus m here. So yeah, the j's with minus m are the z daggers with a positive. So sorry, that's incorrect. And then you can do commutation relations between these ones and these ones. And it's a hard calculation because the z commutator z dagger is equal to this thing involving phi's and phi daggers and unit operators. And there's lots of z's here and lots of z daggers here. So it's very easy to commute these amongst themselves and show that you get basically the SUP commutation relations. And it's very easy to commute these amongst themselves and show the same thing. But when you try to commute one of these with one of these, you get commutator terms of z and z dagger. So we can show that when you do that, you get a horrible, horrible mess, but in the limit that n goes to infinity. So that's the number of electrons that are in the system. Lots of this horrible mess is 1 over n suppressed, and there's just a single term that survives, which is precisely the central term that you need in a current algebra. And in fact, there's this shift of k goes to, usually it's written as k goes to k plus n for UN theory, but my k was defined stupidly as minus everybody else's k. So this is actually we only figured this out when we saw this. So this is actually the correct quantum shift. So we can demonstrate explicitly from the quantum mechanics that this current algebra is there, and you've got the Wess-Zumino-Witten model.
What's the n? Because you have an n with the Fourier algebra, but you're also taking a larger unit.
No, that n is a different n.
Two n's are different.
Sorry. This should be capital N. This is, yeah. This n is the number of electrons, and
Related to the size of z.
yeah, and this n is an index. Sorry, yeah, bad notation.
So this is interesting. Sort of going back to the earlier discussion, Bill was one about what the density operator is.
Yeah.
Right? So these are obviously gauge invariant operators.
Yes.
And in the p equals 1 case, these are the left and right moving. All the whatever the touch movie current. So the density operator must be constructed from these.
Ah, is that right? Okay, good.
Right?
Yeah.
So why do we live on the edge? Or?
So from the sort of the 3D perspective, yeah, there's the droplet, and these are precisely the modes that live on the edge. Yeah. I should also say that from if you just solve this matrix model classically and relate it to vortices, you can see that the classical excitations of vortices are precisely modes which ripple around the edge, because classically this vortex is an incompressible solitonic droplet.
Why is there a tilde in there? I mean, is this approximate?
Where's the tilde? Oh, this means up to 1 over n corrections where the n is this n and not this n.
N is the size of the matrix.
N is the size of the matrix Z, exactly, yeah.
I'm not seeing how
No.
n pressures show up.
This normalization is not correct.
Okay,
Yeah.
there's versions of 1 over n.
Yeah. Well spotted. Good. Yeah. Okay. Other questions? All right. So there's this hint that there's this conformal field theory, and that this simple quantum mechanics is actually capturing the conformal field theory. But there's much more. So this is what Nick did. Nick just sat down and computed the partition function for this quantum mechanics, just exactly. So I didn't think this was possible, but Nick has also been learning lots about integrability, and for some reason that I can't understand, reading obscure Russian mathematics papers from the 1980s, and just managed to sort of put all this together and compute exactly the partition function of this quantum mechanics. So let me tell you what that means. This is the partition function. You trace over all states in the quantum mechanics. T to the E is the energy, and T is what you would usually call e to the minus beta. So we're sort of writing that as a fugacity rather than the usual Boltzmann suppression. And we're going to normalize things so that there's an omega, which is the strength of the trap. Remember that the energies are all proportional to the strength of the trap, buried in here as well. So E is just going to be integer valued. Okay. And then this system has an SUP global symmetry. So we're going to introduce fugacities for the commuting U1 elements of that SUP. Okay, so that's called the Cartan subalgebra. So the X's are fugacities for the U1 parts of SUP, and the J's are the angular momenta associated to those. Okay, so it's going to be an interesting function, which is a function of the temperature, roughly, which is buried in T, and the chemical potentials, which are buried in the X's. So I'm not going to tell you the details. Let me sort of tell you the form of how this works. What you do is firstly, you forget that there was a gauge symmetry at all. And if you don't have a gauge symmetry, these are just free fields. Free fields charged under UN and SUP. And so you write down, for free fields, the partition function for the Zs and the Phis, where omegas are now, so I won't call them omegas, let me call them Ws. Ws are now fugacities for the U1 parts in UN. Okay? So if you were to expand this out, Taylor expand this, you'll get a series, a polynomial in T, and the fact that there's an omega divided by omega is telling you that Z is in the adjoint representation of the gauge group, because it's fundamental, which is like charge plus, with times anti-fundamental, which is like charge minus, so it appears on the bottom. Similarly for the fundamentals, this is the partition function. The fundamentals are in the fundamental of UN and the fundamental of SUP. So this is a UN fugacity, this is an SUP fugacity. Okay, so you put these together. Now you have to take into account the fact that these are gauged, and you do that just by imposing Gauss's law, which you can do basically by a contour integral. So the idea is that you do a contour integral, and you only pick up the pole pieces, which go as 1 over omega, which means that here you need states with k omegas, but the states with k omegas were precisely what was required by that Gauss law constraint. Okay? And this is something that comes from the Haar measure when you go to the Cartan subalgebra. Okay, so this is the form, and Nick just managed to do these integrals. Just did them completely. When I say do them, you get an answer which is in terms of functions that other people know about. Okay, so this is the answer. And if you don't know what these things are, I had no idea what these things are when about a month ago. So the answer is in terms of functions that are well known, where well known means they have their own Wikipedia page. Okay, so you can just look them up and see what they are. There are things called Schur polynomials and Kostka polynomials. And let me tell you the basic structure. The lambdas and mu's correspond to representations of SUP. Okay, so each lambda is a representation of SUP, and mu is some particular fixed representation of SUP. The Schur polynomials are symmetric polynomials in the chemical potentials x1 to xp that depend on some specific representation. Okay? They turn out to be a basis of symmetric polynomials, and they're fairly well known. I think I'd probably heard about them before. The Kostka polynomials I hadn't heard of before, but these are, well, the following. You give me two representations of SUP, and then I hand you back a function of T. Okay, that's the way the Kostka polynomials work. These are very well understood. These are well defined, but not so well understood. Okay, there are web pages that list Kostka polynomials given two representations, but I think there's no closed form expression for these objects for arbitrary representations. No, so what's going on here? There's a sum over certain representations of SUP, which I won't tell you which, but there's a particular list of them. And mu is a fixed representation that depends on P and on K. So, and on N. Depends on all three of those. Number of vortices, P, the rank of the 3D gauge group, and K, the level. Okay. For example, no, I'm going to get the example wrong. It depends in some complicated way. It depends on N mod P. So if N is an integer multiple of P, then mu is it's some very high representation, depends on N. I think it's the nth symmetric product of P, of the fundamental representation. Yeah, the nth symmetric representation of SUP, if mu is divisible by P. And if mu is not divisible by P, it's something else. Okay, so we have this sort of closed form expression for the partition function. I have to confess, we've not, there should be lots of physics buried in this, but we've not tried to extract it yet. And to be honest, I don't really know what I should be looking for. So it's
still some infinite sum, right? I mean, because,
that's right. That's right.
Series, some kind of series representation.
Absolutely, yeah. So, I should say, I don't know if these are understood well enough for us to be able to extract physics in the limits that we want. too. And I don't really know what physics we should be extracting from this. But obviously we've got the full partition function, so in principle, there could be lots of information. So if, I'd love to hear what would be interesting to compute from this. No, it's certain partitions which define the representations. Yeah. Okay.
So back in the electron language.
Oh, yeah.
This is a partition function of some of what?
It's a partition function for these. I don't want to call them electrons because they each have spin, but for these particles moving in the lowest Landau level.
But with edge, so you're also.
It's a finite number of particles. Yeah.
So if it's a gap system in the bulk, then most of the partition function contribution comes from the edge.
That's absolutely right. Yeah. In fact, we saw earlier that the low-lying modes are precisely these currents on the edge. I don't think so. And I can show you later. It's particular partitions which are, in one-to-one correspondence with representations of SUP. So there's a sum over specific partitions. Okay, so this is for finite n for p and k. This is the exact partition function. But now there's something very nice. It turns out that this particular combination of well-known polynomials is also a polynomial, but one that's not well-known. It doesn't have a Wikipedia page. And it's called the Milne polynomial, at least by certain Russian mathematicians. If you Google Milne polynomial, almost nothing comes up. But it's quoted as a Milne polynomial. For some reason, mathematicians studied exactly this limit, or this combination of these objects in the 1980s, and studied what happens when n goes to infinity. I have no idea why they did it, but this is interesting for us. N goes to infinity is having lots of particles with fixed p and fixed k. And if you go to these papers, what they claim is the following. I should say that what I'm about to tell you is proven in certain cases, I think for SUP being SU2, but as far as I can tell, remains a conjecture in the maths literature for other cases, with lots of evidence, but has not yet been proven. So the claim is that if you take, if n is divisible by p, slightly odd, and you take the n goes to infinity limit of the partition function of our quantum mechanics, it gives you exactly the partition function of the Wess-Zumino-Witten model, which is thought to be the edge modes, as a function of the temperature and the chemical potential. So strictly speaking, this is what conformal field theory people would call the vacuum character of this, the Wess-Zumino-Witten model. If you take n not to be divisible by p, but to be equal to some integer times p plus q, where q is obviously an integer less than p, then you take the n goes to infinity limit, you get a different answer. You get what's called the character of the Wess-Zumino-Witten model in the qth antisymmetric representation. So what does that mean? The Wess-Zumino-Witten model is a conformal field theory. It has certain primary operators. If before you compute the partition function over a torus, you insert a particular primary operator in the qth antisymmetric representation, and then you sum over all states, that's this object here. And I should say that there's more in the Wess-Zumino-Witten model. There's other characters associated to symmetric representations, only a finite number of them, and we haven't managed to find them yet. It's pretty clear that it's related to what I mentioned earlier. It's related to somehow putting quasi-particles into the system. So I think somehow you have to put a Wilson line into the original Chern-Simons theory, understand how the vortices respond to that, write down a slightly different matrix model, and then compute it. So Nick told me last week he knows how to do this from the matrix model, but I don't quite know how to do it from the 3D perspective. Yeah, that's right. Yeah. And the level is at k minus p. It's the quantum corrected level. That's right. Yeah. Okay, so this is where we are with the non-Abelian case. We have, I think, very clear evidence that these non-Abelian quantum Hall states are directly related to the conformal field theory on the boundary. Now, there's other relationships between Hall states and conformal field theories that Moore and Reed told us. about how you're supposed to compute correlation functions in conformal field theories, and that gives you wave functions. I have no idea how this is related to that, but I have no idea what that really means or what they're talking about anyway. So I think this is a much more precise way of doing things, and we're really kind of proceeding systematically and understanding, not with all the important details of a real condensed matter system, but at least in this toy model, really understanding how these various things are connected. So we've probably got a few months of work still to pad this out, but I'm hoping at the end of the day we can certainly understand the wave functions, certainly understand the edge states, maybe start to understand the anions and the non-abelian braiding, but directly from these wave functions. Okay, that's all I have to say. Thanks for your attention. No, it's the shift of integrating out the non-abelian gauge fields. It's the k goes to k plus n from the non-abelian. So it's what Shiraz said in his talk. It's the k goes to k plus n sine of k. But my k is minus his k. And capital N for Shiraz was p for me. So it's that standard shift that if you write down an SUN Chern-Simons theory, everything in quantum mechanics goes as k plus n. Because my k is stupid definition. My k, it turns out, is minus everybody else's k. Yeah, it's a positive number, but there's a minus sign in the action in front of it. So it's minus what everybody else calls k. So k me equals k minus k everybody else. Okay. And then if you plug it in, you get the shift minus rather than plus. So it's supposed to be. Oh, actually, that there's something odd there. Yeah, for p, k has to be suitably big. That's right. Yeah. That's right. Sorry, say that again.
It's the ordinary dimension for k that leads to the level k that's level, where k has to be a positive integer.
Oh, you're saying k was. I see. I don't know. It's certainly true that the level of everything is k minus p. Yeah. Maybe you're right. Maybe we haven't understood that. Yeah.
Whatever appears as a central charge has to be prohibited.
Yeah, so presumably if k is not big enough, if k is less than p, this theory, I don't know, does something weird. Oh, no, the theory doesn't have a ground state, if that's true. Because, let me, yeah. Sorry, so remember, there's this constraint, right? And when you take the trace, so the constraint was ZZ dagger plus the sum of I goes from 1 to p, phi dagger equals k. And when you take the trace, you want to normal order these to compute the number of psi excitations. And so the system simply doesn't have a ground state when k is less than p. Yeah. So I see. So the physics is right. K less than p is bad, but I see what you're saying. Matching it to what everybody else is. Yeah, I don't know.
It's not like in the ordinary definition. I would have thought that Chern-Simons level would be k minus p and so k.
Sorry, say that again. You would.
I would have thought that. I mean, in usual versions of Chern-Simons, when the p level is from k from p level to the level k minus p, you also have Chern-Simons p level k minus p, and it's the usual.
Yeah. But you're saying it should shift to k plus p. Okay. Yeah, okay. There's something to understand there. I agree.
Non-Abelian is one direction, but I think in terms of general Abelian chunks, I would say
yes, good. So we've tried to do that. So the problem is if you give me a general K matrix with interacting, I have to do this game where I figure out the dynamics of the vortices and write down a matrix model that captures those vortices. At least that's the way we did it here. So there is a class of K matrices where I know how to do that. But it doesn't seem, from what I've read in quantum Hole literature, to be a particularly interesting class. In particular, it's not, it doesn't give you the first kind of states you would hope to find. And so we have that, but we haven't yet tried to solve it quantum mechanically. It turns out some of the problems you come across in that are related to the non-Abelian problems. So we're doing this first, and then we'll go back. But you're right. In general, I think there should be, sort of what we would call quiver, what you called moose, but quiver quantum mechanics matrix models, where you get to specify, how many vortices in each U1 factor roughly, and then try and solve those. I think that's there to do.
I think the thing has to do with the flavors, because if you had more conventional flavors, the modification, I assume that in the vortex modular space is that you promote these size to matrices with the n by nf.
If you have nf flavors, the first p of them appear as fundamentals here, and then you get nf minus p anti-fundamentals. Yeah. So the others become anti-fundamentals, and then you have another matrix model to solve. It turns out that if you have anti-fundamentals, it's much, much harder to play these kind of, this partition function game. I think just because you have many more gauge invariant states that you can build.
It's not some simple multiplication.
No. And again, it's something we've looked at, but we haven't figured out.